Okay, so the recording is going. Let's see here. I'm going to share now. Here is the screen. Let me know if you can see that, if you can see my screen. Okay, great. Well, welcome to Human Hour Volume 3. I apologize if I'm a little bit nasal. I'm still feeling a little bit under the weather, so I apologize if the audio quality isn't great, but feel free to unmute yourself and ask for clarity or anything like that. I mean, I think just because there's so few of us here, feel free to unmute yourself and ask any questions along the way. This can be kind of very informal. So yeah, today we're going to be covering just sort of the basics of smart contracts and Solidity. And I think as I was sort of going through this last night, I think it might be interesting to kind of just give a quick high level overview of sort of the Ethereum ecosystem, as that's kind of really important for understanding sort of how smart contracts work and what they do. So the first thing I want to sort of cover, or at least look at, is kind of like how the Ethereum ecosystem works. And when you think of doing something like buying an NFT, a lot of that sort of what happens behind the scenes is hidden away and abstracted because you just sort of interact with MetaMask. And what a lot of people don't understand is sort of how things work and sort of what's communicating with what. And so this is just a very basic diagram that sort of tries to show the process. And when you go onto OpenSea, for example, you sort of log onto the website, and then you want to buy an NFT, so you open MetaMask. And what MetaMask is doing when you sort of click buy on your NFT and it asks you to sign a transaction, you're not communicating directly with the blockchain. You're speaking to something called an RPC node. And an RPC node is essentially just a server that is running somewhere, and you're communicating it through an API, which is an application programming interface, which most people sort of should have heard the term before. It essentially just gives you programmatic access to like a service. So for example, like something like, I don't know, let's use a random example, like Uber or something. Like if you wanted to build a website and include some of Uber's information or functionality on your website, you would access that through Uber's API. So they control what information you have to their server. So when you create your transaction or you're trying to buy, you're making an API request to an RPC node, and that RPC node is then going to push your transaction details into the mempool. And the mempool is basically it's an area where all transactions essentially go to wait. So when you, for example, in situations, I'm sure it's happened to everybody, where you set your gas too low and you're waiting for your transaction to go through, but it's just sort of sitting there, nothing's happening. What's happening is that it's actually just it's sitting and it's stuck in the mempool, or it's not stuck rather, but you're waiting for miners to pick it up and process it. And that has a lot to do with the gas fees and how miners work, which we'll get into a little bit later. So essentially what happens is you create your transaction. So you say, I want to buy such and such NFT. This is the price I'm setting. This is the gas. That transaction goes and sits in the mempool. And if the gas price is high enough and it's worth the miner's time to process your transaction, what they'll do is they'll pick that up, they'll process the transaction, and then they'll stick it into a block. And then that block goes into the blockchain. And once that transaction has been confirmed, then that's when you get your, sort of the NFT purchase or the transfer or whatever you're doing takes place. And that only takes place once the transaction's been mined and that actually appears in the blockchain. So you might have heard the term EVM, or Ethereum virtual machine. And basically what that means is it's a virtual machine. So it's a sandboxed or isolated environment that's used, that's a runtime for running smart contracts. And essentially what a virtual machine is, it's a virtual system, like a little operating system or a set of programs that is running on a piece of hardware, but it doesn't actually have any access to that hardware itself. So it can't access the network, it can't access the file system or anything like that. So it's essentially a little sandboxed environment. And with the EVM, you get two kinds of accounts. You get externally owned accounts, which are like user accounts. For example, and these are often referred to as EOAs. You might see that written. And what these externally accounts are is they are the account that you see is the public key of the key pair. So the private key is what you use to sign your transactions, and the public key is what makes up your Ethereum address. And then the second kind of account is a contract account. So when you deploy a smart contract to the Ethereum blockchain, it also creates an account and it gets its own address. And it differs from an EOA account to an external account because that address does not have a private key, at least not in the way that we're used to seeing. So here is I just wanted to show you a fun example of a visualizer to show you what's sort of going on. So this is a fun visualizer, and it's showing you what's happening on the Ethereum blockchain right now. So if you remember me describing going to the website and creating a transaction, and those transactions go into the mempool, that's essentially what you're seeing represented here. All of these little characters that are sitting on the side, and this is all happening in real time. So this is an actual description or view of what's going on in the Ethereum blockchain. So all of these little characters are all people that are transactions that are sitting in the mempool, and they're waiting to be picked up by miners and added into the blocks. And this is the actual blockchain that you can see here. So these are getting processed one by one, and you'll see as sort of more are coming from these different services. You can see the mempool's filling up again, and it's adding them to blocks, and it's moving them away. So that's just a fun little, I'll share the link. So this is a fun little thing to explore. And then just by comparison, you can see this is the Bitcoin blockchain, and you can see sort of the differences and how, for one, how much less traffic there is, but two, for sort of how much slower it seems to move. So now that we've covered that, I also just wanted to share this is a pretty good resource. Again, I'll share links to all of this, but I recommend everybody reads this. And it's just describing how your public and private key pairs work. And essentially, you use your seed phrase, which is the thing you should never share. The seed phrase is used to deterministically create your account and your private keys. And what that means is that you can recover any of your Ethereum addresses using your seed phrase, no matter how many accounts you create for it, because it's deterministic, so it always knows what to expect. And the passwords, all the password for MetaMask does is it gives you access to your account. So the password doesn't have any effect on your public keys, your private keys. It's simply a way for you to prevent people from accessing your MetaMask wallet. But you can always recover your private key or your public accounts as long as you have your seed phrase, which is obviously why it's so important that you never share it. So just to go back quickly here to cover, so as a reminder, an RPC node, RPC stands for Remote Procedure Call, and it's a way of executing functions basically a way of executing functions or pieces of code on sort of a remote server. So that's what MetaMask is allowing you to do when you're creating transactions or sort of purchases or sales, is you're essentially executing code on a separate service. So for example, like your dApp or MetaMask, when it executes a transaction, you don't speak directly to the blockchain. Instead, you're communicating with the node that itself is responsible for reading blockchain data or sending transactions to the network. So now that we've covered that, let's take a quick look at, well, not a quick look, we'll take a somewhat in-depth look at Solidity, which is the language we use for creating smart contracts. So a really easy way to get set up with Solidity or to start playing around is there's a browser-based IDE, which is an integrated development environment, which is accessible directly through the browser, and it's called Remix. You can just Google it. or the URL is pretty straightforward. It's just remix.ethereum.org. And let's go here. So let's create, for the first time, we're going to create a brand new contract. Let's just call this my first contract .sol. So you can see we're creating this as a .sol file, and the sol file indicates that we're going to be using Solidity. And just a quick overview of what Solidity is Solidity is a language that is essentially inspired by languages like C++ and Python, which are object-oriented programming languages, often referred to as OOP, which means they sort of you can use classes and inheritance, so you can sort of define an object, and then you can create another object that inherits from that object, which sounds a little bit confusing, but we'll go through that shortly when we sort of start writing some code. So what exactly is a smart contract? I mean, a smart contract is essentially just a program or a digital contract that gets stored on the blockchain. So you write some code in Solidity which we'll be using. So you write a program or an application, I think rather let's refer to it as a program, that then gets compiled down to bytecode. So maybe we should just go into that quickly, just to sort of explain before we start writing our own contracts. So something that's really important especially with sort of NFT projects, or when you're looking at a DeFi project or something, you really want to make sure that you can read the contract code for whatever you're interacting with, which is sort of the whole benefit of blockchain, is that everything is transparent and you can see what's going on. So if you take a contract address, so for example, this is the contract address for the Humans of NFT project, and you go to Etherscan. So I skipped a couple steps. Let's just say if you know the contract code, or the contract address rather, sorry. So you can search this, you can put it in here, and it'll show up. So this is essentially using Etherscan to see all the information available for this particular contract. And if you remember when I was talking earlier, when you deploy a contract itself gets its own address on the Ethereum blockchain, and that's exactly what we're seeing. So you're telling Etherscan, I want to go and see what's stored at this address on the chain, and it's returning all this data and says, okay, well, there's actually a contract that's found here, and here's all the information pertaining to that contract. So once you've loaded it, the next step you want to go and do is you want to go to the contract, and the contract actually allows you to read all of the code that's written. And now something that's really important is, for example, so what we're seeing here is because we can read the actual code, it means that the code itself on Etherscan has been verified. And you can see that over here where it says the contract source code is verified. And what that means is that the deployer, or the person who's put that the code on there, has basically gone through an extra step and said, hey, I want this to be transparent. I want people to be able to see what I'm doing and read my code. So you go through the process of verifying it, and then it shows that everything is available here and you can go and read the code. Now, some people and some projects choose not to verify it. Nobody can sort of speak to what their motivation for doing that is, but contrary to popular belief, you're still able to read the code. Everything is still publicly available. It's still sort of transparent, even if you've made some sort of effort to obfuscate it. So, a project, maybe it's not necessarily all projects that have unverified contracts are bad. People might have their reasons, but it's generally best practice that people show or verify their contract. A very good example of this so this is the contract address for OpenSea's shared storefront. And from what you can see here is this is what it looks like when a contract is not verified. So what you're seeing here is the bytecode. So the bytecode is essentially a lower level representation. It's basically designed for like a machine or a computer to read. This is not supposed to be human readable. It's sort of like all of the information packed into essentially like as small a space as possible to make it more efficient. But the downside is that it's not human readable. So, Who knows why OpenSea has chosen to keep their contract unverified? You and I can only guess. But the point is that because it's the blockchain, um, there are ways to read this. So there are a bunch of tools out there. And again, I'll share links to this. I'm going to just have a look at this ethereum, which is a decompiler. So this allows you to decompile bytecode for unverified contracts. So let's take this one, for example. Here's the address. I'm going to go and put it into the contract address, and then I'm going to select to decompile it. And what's happened is this decompiler has basically, it's doing the inverse process of when you when you write a smart contract and you compile it, it goes from Solidity into bytecode. There are a few steps in between, but for the sake of simplicity, we don't need to go into that. But essentially, you go from Solidity and you end up with bytecode. And what this tool does is it allows you to go in the opposite direction. So it allows you to take bytecode and decompile it into Solidity. So this gives us a pretty good view of what's going on inside of the OpenSea contract. These are all of the functions that happens in Solidity. So what happens with some people, or in some situations when somebody deploys a malicious contract, you'll get sort of like really smart people who know what they're doing and who sort of know how to read things, who can go and take that unverified contract, for example, this, put it through a decompiler, and then actually deconstruct what's going on. So for example, like there are all these situations where people are sort of where they have their Bored Apes stolen because they're signing malicious transactions. What's actually happened is somebody has created a contract that has a method inside the contract that says, if somebody approves this, then transfer tokens out of their wallet. And a lot of the times when that happens is you'll see those contracts get deployed. They aren't verified, so that all you see is bytecode, so that if someone is about to sign something and they think, oh, maybe I should go and check the contract, and they come and have a look here, it's usually a red flag if you're going to a contract and you're not really sure of the source. If you can't see the source code, it generally means that somebody might have bad intentions, because they're trying to obfuscate or at least hide what that contract is doing. But again, every use case is different. I make it a rule of I won't interact with any contract or with any project unless I could read through the source code myself, to at least get a sort of good idea of what's going on. So just to come back to the humans contract, you can see once this has been verified, then it now shows you can go through and read all of the code. And then on the upside, once it's been verified, this also allows you to interact with the contract. So you'll hear a lot of people with projects, like perhaps if their website goes down, maybe you want to mint, they tell you to go and mint through the contract. You can either do it by sort of writing a script or writing a program, or you could come to something like Etherscan. And for example, let's have a look here. And if we want to get the token URI for a specific, well, maybe let's have a look first. Sorry, let's go to the code. And inside the code, you can see in the humans contract, let's go and have a look for the token URI function. So this function is going to return the token URI for any given ID. And what this means is it's going to show you the location on a server somewhere or on IPFS where the ID is, where the metadata for this token is located. So we can see that the token URI function, so if we want to actually go and see what's happening, we can go into the contract, we can go find the token URI function, and then let's say, let's go and find the URI for token 263. You can query it. Oh, this hasn't been minted yet, so let's say maybe token 1000. So here is the IPFS metadata URI for the token 100. So the same thing could happen if, let's see, if you wanted to perhaps mint. Let's have a look. Mint price. So say we wanted to get the mint price. This is going to return the mint price in Way, which is the smallest unit of Ether, which again we'll cover shortly. So that's a quick overview of sort of viewing smart contracts through Etherscan. So now we can go back to Remix and we can actually have a look at writing a little bit of Solidity ourselves. So Again, as I mentioned earlier, Solidity is just a language. It's a programming language that allows you to write smart contracts. Before you deploy the smart contract, it gets compiled into bytecode, which is what we showed you earlier. And then once it's been deployed, you would go through the process of verifying it. And then once it's verified, everybody would be able to read the code for your smart contract. So again, this is Remix, which is a really incredible tool and amazing for just sort of playing around and getting sort of used to everything. Which is a little bit more advanced if you sort of get to the point where you are wanting to sort of write and test your own smart contracts. There are other ways to do it, which are generally more preferred by developers, sort of using a local environment. There are tools like Hardhat and Truffle, which let you write and test your smart contracts that you're developing and deploying. So a quick note on what's going on here is this platform, or this IDE, sort of gives you everything built in. So what that basically means is that you're going to be deploying, as we test things, is it spins up its own local version of a blockchain. So when you're doing this, at least when you're developing with Remix, you're not deploying anything to Ethereum or to any of Ethereum's testnets. It's only going to be running a local version of the blockchain. So there's no other transactions from the outside world that are taking place on it. It's just your own personal little miniature blockchain that lets you test and do everything you need to do until you get to the point where you want to deploy it. So let's just have a quick look at some. Yeah, yeah, sure. Yeah, feel free to stop me at any point. Yeah, go for it. Or not. Is there anything you wanted to ask? Okay, I'll continue, and feel free to stop me and interrupt at any point. I really don't mind. I'm just sort of winging this, so if there's anything that's not clear or I'm going too quickly, um, yeah, feel free to stop me. So let's have a quick look before we start writing any code at some of the settings for Remix. So over here, what it's asking us to set our version of to have a look at which compiler we're using. So the compiler is basically the piece of software that comes built in with all of these IDEs that is going to convert your Solidity into the bytecode that I showed you previously. And like any other, like any piece of software, it changes over time, it gets improved, people patch bugs, so different versions are released. So what you can see here is you can choose which compiler version to use for your code. So let's just choose the, whatever was set by default, 0.8.7. We're choosing our language, which is Solidity. And then the EVM version, we don't really need to worry about this. We're going to let the compiler choose it itself. So now that we've chosen our compiler version, we can actually go and write some code. So this is our IDE, and basically all you need to do to create a smart contract in Solidity is define a contract with the word contract. You give it a name, and you enclose it with some curly brackets, and that's technically it. This is technically a smart contract. It doesn't contain any code, it doesn't do anything, but this is everything that you need in order to write a smart contract, at least in order to define a smart contract. So we can go over here and we can choose to compile the contract, which is converting it to bytecode. And that's it. All it's really done is it's taken this Solidity language file that we've created and it's compiled it into bytecode that can then be deployed to the blockchain. Now, the IDE is doing some useful things here and it's giving us some warnings. And what it's telling us is that we're missing a license file. and we're missing the compiler version. And these are both pretty important. So the first thing you generally do when you write a smart contract is you want to tell the compiler what version of Solidity we're going to be using. So if you remember here, we chose the compiler. If you can remember here in the compiler settings, we chose version 0.8.7. So what we actually want to do in our code is that we want to tell the compiler what version we want to be using. So we're going to say pragma solidity 0.8.7. And all this means is pragma is a directive that is telling the compiler that this is the version of Solidity that we want to use. So anytime you go and look at a smart contract, so for example, let's go back to the humans, you can see the first thing that's declared in the file is it's telling you what version of the compiler is being used. And then the second important thing is the license, which is just telling anyone who's reading the contract what the license is. We won't go into what the details of the different licenses are, but for now, let's just use the MIT software license and include that. So now if we go to compile this, you can see those warnings are no longer there, but it's also just, it's giving us basically some issues and saying that, there's no code inside. So what are we going to do? So the first thing we're going to include, which is important in every smart contract, is just to include a constructor. And a constructor is simply a function. Why is it complaining about this? Sorry, this is the one that needs a... Forgot to mention that in Solidity, in certain languages that are strongly typed, you have to end every line of code with a semicolon so that the compiler knows that you've put an end to the statement that you're creating, because you can break things over multiple lines to make them readable. So you need to tell the compiler that at the end of the contract, at the end of the statement, this is the end of the statement, and you don't need to continue reading anything that's underneath. So here we have our minimal version of a smart contract, and this is it. I mean, this is basically a smart contract if we really wanted to keep it this way, and we could compile this and we could deploy this to the blockchain. So what I've gone and done here is under this little section on the sidebar, which is deploy. This gives you the option to actually deploy the smart contract. So I've written this incredibly basic smart contract that does nothing at all. And what we've done is we've gone and we've taken and we've deployed it. And you can see down here, see if I can expand this. This is giving you the console output of what's happening. So you can see here, it's telling you this is the creation of my contract is pending. And then the transaction has been mined on on this little local blockchain, and it's created the contract itself. And you can see here under deployed contracts, here is my contract that's been created, and it's got an address on the local blockchain. So you can always copy this and you can have a look. This is the address that our very, very basic contract has been deployed to. And if we were going to deploy this to the mainnet, to Ethereum, we could do so. You can see here it's asking us where we wanted to deploy it to, and this is just a JavaScript VM. So this is a local version of the blockchain. You could, of course, always connect your MetaMask wallet to this, to the Ethereum mainnet, using sort of Web3 provider, and this would allow you to actually deploy from Remix in this IDE onto the mainnet, onto the Ethereum mainnet. But that's never a good idea. As I mentioned earlier, sort of most developers choose to use their own sort of tools and set of tools which are running locally. And in general, you would want to deploy sort of a production version of your contract from your own machine, where you can set up, deploy scripts and build scripts and things like that that are going to allow you to sort of control doing everything the way that you want to. So now that we have our very, very basic contract, let's have a look at making it slightly more interesting. So let's say we wanted to create a smart contract that kept track, that was essentially a counter, and it just kept track of a number. So every time somebody did something, you want that contract to keep track of the number that's changing. So we can declare a variable. We're going to create a uint256, and we're going to call that a counter. And then let's say we want to set the, okay, I'm going to do a few things and then I'll explain them step by step because there's quite a few things going on here. So we'll create a function and let's call this increment counter. And we're going to make this counter increase. Okay, so before I go through it line by line, let's try deploying this. I guess first we should compile it. Let's set it to auto compile so that every time I save the file, it's going to compile it. So we'll compile the contract. Then we'll go to deploy it. And now we've deployed this contract. And again, you can see what's really nice about Remix is that Remix exposes the functions that are in your contract, and it allows us to push a button. And every time I'm doing this, it's calling the increment counter function, and it's actually increasing the count. And you can see here in our console, what it's doing is it's logging and it's telling you that these transactions are being processed and mined. Now, generally what happens, like with Ethereum, is what we explained earlier, is that you submit a transaction, it goes into the mempool, it has to get mined, and that usually takes a while. Like you've seen, sometimes you submit a transaction and it takes 30 seconds or 5 minutes, or depending on the gas price that you set. Because this is a local blockchain and it's running in our own little virtual environment, there are no other transactions taking place. So everything happens immediately, which is also obviously also really nice. Because you don't have to wait for things to process or for miners to process transactions while you're waiting. So let's go through this line by line and see what's happening. So another thing I wanted to just point out quickly is, which you've probably seen before. So let's maybe go back to the humans, and you can see we have these what are called comments in contracts or in code in general. And this lets you sort of add little notes, either for yourself or for the person reading it, that don't get processed by the compiler. So they're not included in the code itself. They don't affect how the program runs. Instead, it just adds some information for you to see. So we can do that for ourselves. So we can say, let's just say, counter is a variable that keeps track of how many times you've counted something. So perhaps the first thing to point out is that we're using this type uint256. So a uint is an unsigned integer, and an integer you can think of as a whole number. And the fact that it's unsigned means that it can only be positive. So if this were just going to be an integer, let's say some integer, this could be 0 or 55 or 99, but it could also be negative. So this could be -99, -555, anything like that. And depending on what you want your application to do, whether or not you want to use negative numbers. But in general, with most smart contracts, you'll see people using this uint256, which means it's unsigned, so it can't have a negative sign, is an easy way to think about it. So it basically means that this number will always be 0 or positive, and then the 256 is indicating that it can store 256 bits of information. So if you think of maybe the easiest way to explain this is color space. So if you've ever seen something that's RGBA or RGB8, basically means that this is an 8-bit color space. So it stores 8 bits of information. And a bit is sort of the lowest level that a computer stores information at. And a bit is binary. So a bit can either be 0 or 1. So when you have people talking about computers and they're talking about bits and bytes, a bit is basically the smallest unit, and it can only be either 0 or 1. So an 8-bit number is made up of 8 bits. So it'll be 1, 2, 3, 4, 5, 6, 7, 8. So this uses base 2 counting. So let's have a look quickly if you want to use base 2 unit converter. So let's say from base 10. So base 10 is the number system we use, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then, or I mean, actually rather 0 to 9, not 1 to 10. So let's say we wanted the number 99. The number 99 in base 10 would be 11000011. So this is 8 bits of information. So the important thing to realize here is that this stores a maximum of 256 values. So when you have a RGB8 color, it means that you can only have between 0 and 255 as values, because an 8-bit integer can only hold up to 256 values. So what it's telling you, what a uint256 is telling you, is that it's can hold up to 256 bits of data. So that's a lot of zeros. Basically, a uint256 can hold a very large value. So something you can go and see is if, let's see, NFT, the Genesis collection. So this is minted on OpenSea shared contract. So it's an ERC1155. So this means that the token ID is a uint256. So if you go and have a look, that is what a 256-bit integer looks like. So you can see that it stores a very, very, very large number of values. So that's a little bit of a segue. Basically saying that if we wanted to store value in a counter, we could store a very, 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 very large number, and we could be pushing this button a very long time until we sort of reach that limit. So let's go back to what we were looking at. Then the constructor function is a function that runs when the contract is created. So basically, when a contract gets deployed, so the very first time when you create it, when it gets deployed, this constructor function is being called at that very first time. So when you go and you read a contract, let's go and have a look for the constructor. You can see that the variables being set or defined, or sorry, not defined, that are being set in the constructor, these are being set the very first time that the contract is being deployed, or the only time the contract is being deployed. So those, you can pass arguments into the constructor when the contract is deployed. So this basically, this function is saying that when I deployed the humans contract, I wanted to set the URI, I wanted to set the admin signer address, and I wanted to set the OpenSea address. And the way that I did that is when I deployed it, I provided those values so that when the contract gets deployed, it's assigning those values that I passed in to the variables that we have declared in the contract. So as an example, if I wanted to say, we wanted to give this a starting value, then I could pass that in the constructor and say that the starting value for counter is going to be whatever I pass in. So that might look a little bit confusing, but if we go back to deploy the contract, now where we deploy the contract, it's asking us, so this should fail if I try and deploy it without a value. So you can see that because our constructor now is expecting an argument, it's expecting us to give it a value. If I don't provide that value, I'm going to get an error, and it's telling you here that error encoding arguments, error invalid big number. So it's telling me that there's an invalid number, and there's an invalid number because I haven't entered anything there. So let's say that when I deploy the contract, I want the counter to start at 99. Let's just get rid of this because it's a little bit confusing. Let's say we wanted to start it at 99. When I deploy that contract, what it's going to do is the very first action it's going to take is it's going to set the value of counter to 99 to whatever I passed in. Now, something that's interesting is that now that we've deployed this, there's no actual way for us to read what this data is. So this, every time we call this increment counter function, it's going to increment the value and it's going to store that. It basically gets stored on the blockchain, but there's no way for us to read it, which is not very useful. And this now comes into what we call visibility. And all we need to do is we can add the keyword of public here. And if I deploy this contract again, let's set it to maybe 88 this time and deploy it. Now when we go and have a look, there's something interesting. And now we can see that on the contract, it's given us an interface to this thing called counter. And now this counter is the variable that we've created. So if we click it, you can see that it returns the value of 88 that we've set it to. So what you can think of when you deploy through Remix is it's basically creating an interface for you to interact with the contract and its variables in the same way that, I guess you could make the analogy like if you, on Etherscan, if you're reading the code, that is this part of the text editor part of Solidity. And if you want to go and and if you want to go and read the contract, Etherscan is giving you an interface to interact with the contract in the same way that Remix is giving you a way to interact with the contract. So the important point here is that by making this variable public, we're making it accessible to any interface that is outside of the contract. So by interacting with counter, that's going to return this value that's stored in the storage of the actual contract. So now we can go increment counter. You can see it's mined that transaction. So what that's gone, and sorry, this is shorthand. The plus plus, if you're not familiar with programming, is just a way of saying counter is now equal to counter plus 1. So the plus plus is just another way of writing plus 1. Well, technically plus equal 1. You're incrementing it by a value of 1. So what we expect, yeah, sure. Well, okay, so it's a good question. So another important point. So let's do this. Let's say we're going to create another counter and we're going to say this one is private. We're going to create a private variable. We'll call this counter. Let's call this one counter A and this one counter B. So you'll see this in contracts. Then we just want to say this is counter A, and then we want to increment counter A like that. So you'll see this in contracts, this sort of difference between public and private. And, so you'll see that, for example, in the humans contract as well. You'll go through, and if you see all the variables that have been set, we have some that are private and some that are public. And now the important thing with Solidity and with blockchain is that nothing is private in the sense that you can't see it. What these visibility or sort of accesses are dictating or indicating is that it has to do with who can access the information, not whether or not you can see it. So a private variable doesn't mean that it's private and nobody outside can see it. It just has to do with who can interact with this variable. So we'll get to that. But for your specific question, like, you don't pass code per se into the constructor. You're just passing in values that you want to be assigned to variables. So you could, so let's say, for example, trying to think of a good use case, like maybe someone wants to say, so this is maybe a good example. So let's say there's an NFT collection and they say publicly, in their Discord or whatever, we're going to have a max supply. And we're going to have the max supply. Let's make this private maybe. And we're going to have a max supply of 10,000 tokens. So they're telling everyone in Discord and Twitter, and it's like, we're going to launch this collection. It's going to have 10,000 tokens. But then they come in here and in the constructor, they say this before they launch, and then they launch the smart contract. And then you go and you say, then when they set the max supply equal to supply, what they could do is they could tell everybody that the max supply is going to be 10,000, but then when they go to deploy the contract, they could go and say, well, I'm not going to do 10,000, I'm going to do 100,000. And they could deploy that. So that would then mean that the max supply of the tokens is set to 100,000. Now, what is a little bit tricky is because this variable is private, it doesn't give you a way to view it immediately sort of through the interface like it's provided. However, for anyone who sort of knows how to look or where to look, it's very easy to go and see through the transaction what that value that's been passed in is. And so while it might not necessarily be publicly visible in that, like, you can't just look and see straight away, it's relatively simple if you know what you're doing to pull those values out of the contract. So anybody could go and see this and be like, okay, well, they said it was going to be set to 10,000, but after going and sort of like investigating a little bit, they can see that it's in fact being set to 100,000. Then you could then go and say, well, okay, well, this hasn't been a very transparent way to do this. Whereas what they should really do is, if they say we're going to set it to 10,000, that should be set outside of the constructor so that when the contract's deployed, they have no control over what that gets set to. Does that make sense? Yeah. So there are a couple more things I wanted to go through, but I want to be conscious of keeping everybody too long. Obviously, we're not going to be able to go through the whole of Solidity, and sort of like Solidity is a programming language in this short space of time, but some other variable types to look out for are, which are pretty common, as you will see, strings. And a string is a string of characters, so that'll contain something like text. More common ones are a bool, which is a boolean. Let's say this, for example, is live, and a boolean can be either true or false. It only stores that data type, so it can either be true or false, and you use bools for sort of checking conditions on things. Then you have arrays, and arrays can be of certain types. So let's say my array. So this is an array which is a list of uint 256. So this you would be able to contain a list of, well, maybe let's not use this as an example. Another type is an address. So my address, and then as an array, let's say this is going to be an array of addresses, which you declare an array using square brackets. And then let's say this is going to be the allow list. And then what you would do is, you would have some function that lets the owner of the contract add a whole bunch of addresses into this allow list. And then when somebody goes to mint, you would be able to check whether or not they're there. The other probably most important thing, or most common one that you'll see, is a mapping. And a mapping is a key value, allows you to create a key value pair. So the way that you create a mapping is you say mapping, and then in parentheses, you dictate the two kind of types that you want to do. So let's say, which I'll explain now, let's say the key is going to be an address, and the value is a uint, and this is going to be called, let's just say this allowed mints. So what this would look like is this would look something like this. So, just pretend this is going to be, well, let's maybe use this as an example. So let's say this would be the address, and then this is the number of mints it's allowed. So let's say this one is allowed 1. And then let's take another address and say this one is allowed 2. Or 3, whatever. So the mapping is basically, it's a data structure that lets you store a list where each entry in the list is of a specific type. So for example, this mapping, the entries are of type address, and each entry stores a value that's a uint. So a mapping that has with address and uint would have a long list of addresses, and to each address you have mapped a value like that. So that's something that you'll go and see, that you'll see very often in a lot of different contracts, because it's a way of storing sort of large amounts of information when you need to be able to relate that information to something. And then again, quickly, just to look at the visibility. So you get 4 types of visibility. So let's say let's just call this, for lack of something else, this is going to be function A. This is going to be function B. This is going to be function C. So the different types that you get are, there's public, external, internal, and private. And the same goes for variables in terms of their visibility. So something that's public is accessible both inside and outside the contract, and by anything that inherits this contract. So inheritance is a relatively complex topic, which is a feature of object-oriented program, but a really simple way to think about it is that if you had a type, or a class, let's say you get a contract that is a car, contract that is a car, and then it has some logic in here relating to a car. Let's say maybe it has a function that says a function called drive. Then let's say you have another contract. Now, this is a way of sort of sharing functionality between different contracts. So say you have a contract that is type car, and this is how sort of NFT contracts work. I'm sure you've all heard of OpenZeppelin. OpenZeppelin is a set of libraries that pretty much everybody uses when they create their contracts. And what they do is they provide a bunch of base contracts that you can inherit from. So they do this sort of equivalent of this in saying that we're going to provide you some functionality. For example, as a car, every car has the ability to drive. So every time I create a contract that I want it to be able to drive, I don't want to have to rewrite that logic all the time. So it allows you to use something called inheritance. So then you can create a contract called Ferrari. And then instead of saying, I want to have a Ferrari, I'm also going to have to create a function called drive. Instead, what you can do is you can say, contract Ferrari is car, and then you can have in here drive really fast, and this will allow you to call the drive function from the other contract. This is a bit of a confusing topic, and I'd love to go into it more, but just if you can understand it on a very high level, that inheritance allows you to take one type of contract and inherit from it by saying it is. That's just the keyword that's used. That allows you to use all of that functionality that's inside the contract that you're inheriting from. And a good example of this is when you go and look at a NFT contract, for example, the humans contract, you can see that the contract human is an ERC 721, it's an ERC 115 holder, it's ownable, and it's randomly assigned. What it means is that this human contract is inheriting all the functionality that comes in these other contracts. So you can see here, this is the ERC 721 contract. This is the contract that defines the standard, the EIP 721 standard, which dictates what an NFT is and what it does. So instead of me having to rewrite all of that functionality, all I do is I say my contract is an ERC 721, and it inherits all of this functionality. So my contract has access to all the functionality that an ERC 721 contract does without me having to write any of that code myself by simply inheriting it. So that's a really quick overview of how inheritance works. And that's relevant, because that has to do with this visibility. So when we look at something that's public, it means it's available to, anything that's public is available everywhere. It's like somebody outside the contract can view it, other functions and variables inside the contract can view it. Whereas an external function or variable is different, where this can only be, only be accessed outside of the contract. So I could call this function A externally, but I wouldn't be able to call it inside the contract. So for example, I could have some function here that says do stuff. And in here, because this is public, I could call the increment counter function inside of this. However, if I wanted to call function A, this wouldn't work because I've explicitly dictated that this function is only available externally. So you can't call it from within the contract because it's only intended to be used from outside of the contract. The opposite is true with internal. Can only be called inside the contract. So for example, you can't call this method outside the contract. This is only for internal use only. However, because it's internal, this can be used by other contracts that inherit my contract. So if I were to create another contract that was called my super contract, let's say contract, my super contract is my contract, then because this function is internal, I would still have access to it inside of this contract. So I could still call function B inside here if I wanted to. And finally, private is only accessible from within this contract. So unlike internal, if I wanted to call function C from my contract that inherits from it, this would not work because C is private for my contract. So that's a really quick overview of sort of the visibility of functions. I know that was really quick, but I do want to go through one last thing. Obviously, if everybody, you need to drop off, please feel free to. I'm going to continue recording because what I want to go through now quickly is just to help you understand how gas usage works in relation to Solidity and to smart contracts and sort of like what's going on behind the scenes when you're setting your gas price and that sort of thing from Etherscan. Not Etherscan, sorry, from MetaMask. So let me just get rid of a bunch of this because it's not necessary. I'll keep counter A. We don't need to set anything in here anymore. We'll get rid of all of these. Okay, so let's go back to, let's clean this up a bit so we don't have these distractions. Okay, so this to me at least is pretty interesting, which hopefully you might find somewhat interesting too. So let's go back to our very basic contract. Now we have a counter and we can increment that counter using this function that's publicly available, and you now understand what publicly available is. So let's deploy this contract again. We can see our counter is at 0. So I guess a quick aside, an important point about Solidity is when you don't declare, so when you declare a variable, so we're declaring a variable here and saying this is counter A. What you would normally do in if you wanted to give this a value is you would say, I want this to start at 0. However, with Solidity by default, for any integer, it always instantiates or starts this value off at 0. So when we deploy this contract by not giving it a value, we're automatically telling the contract that we want you to set this to 0, or we know that you're going to set this to 0 and that's going to be okay. So when you check the value of counter, you can see that it's at 0. So let's call increment counter. Now we can see it's at 1, increment counter at 2. Okay, so now this is where things get interesting. Now, for most people, this idea of gas is like a real mystery. It's like they understand it as it's this thing on MetaMask that I have to change in order for my transaction to go through. But why is that the case? So what's really interesting is we can go and debug this function, or we can debug this contract. And what this is going to go and do is this is a very low level feature that allows you to step through the sort of like the very low level of the contract piece by piece if you're going to try and debug it. But what's most important is that when you compile a Solidity contract, it compiles into bytecode. And the way that the EVM, or the nodes that are the processing or running that code, the way that they see that is they see it as these things called opcodes. And you can see that these are the opcodes on the left-hand side. Now, this is a very, very advanced topic in terms of like how Solidity works, so we don't need to go into that. But basically, if you can think about opcodes as these are the very, very, very lowest level of instructions on what your Solidity program that you're writing, it gets compiled and broken down. Solidity is like a very abstract language. Like you're using human readable words to say, I want you to increment this counter by value 1. A machine doesn't understand that language. A machine understands like very specific instructions. So when your contract gets compiled, it gets compiled basically down to the lowest level, which is just a set of instructions called opcodes. And now what's really interesting about Solidity, which is different to sort of most other programming paradigms, is that each of these opcodes has a cost associated with it. And this is where gas comes from. Or this is sort of what gas is used for. So let's see if we can find opcode gas costs. Let's see, opcode gas costs. Yellow paper. I should be able to find a table somewhere. Okay, so there is I can link to it as well. Is this the revision spreadsheet? Okay, so again, this is not something you're ever going to have to use or really even understand, but I just think it's really interesting to explain how Ethereum works and sort of how gas costs work. So here, for example, is this is a table of what all of these different opcodes cost. So one of the most expensive things in Solidity and sort of when you executing functions on smart contracts is when you're reading and writing values to storage. So that means like when you're adding an address to a list, that's going to cost a certain amount of gas. So for example, the amount of gas used for S-load, which is storage load, so this is to load a value out of memory, costs 200 gas. So not that you need to sort of know that, but basically every instruction that you can see here that gets executed has a gas cost associated with it. So every little step in this set of instructions costs a certain amount of gas. So what that means is in order to execute a specific transaction or function in a smart contract, it has a very specific gas cost in terms of all of the instructions that need to get executed in order for that to happen. Now, what's really interesting is that when you go and, for example, let's go to humans of NFT. Let's say we wanted to buy a human. This is obviously a fake collection because this is in Polygon. We should report that. So let's say we wanted to go and buy this human. We'll go on OpenSea. We're going to say buy now. Okay, so this is what everybody is used to seeing, right? You go to buy something on OpenSea and MetaMask pops up and it's like, okay, this is how much the transaction is going to cost. And for people who are a little bit more savvy or who have sort of a little bit of experience, you can go and you can edit the gas that you want to pay. Now, what's interesting is that I'm sure if you've read or seen instructions and it tells you never to change the gas limit in terms of what the transaction and what the gas limit essentially is it's MetaMask is sort of through a bunch of mechanisms that we don't need to explain, it's estimating what the cost to run this specific function of, which is going to be, for example, in this contract, it's going to be to transfer from user A to user B in sort of the simplest sense. And it's estimated that it's going to take a total of 253,000 gas to execute all of the opcodes that are involved in that transaction. So in order to estimate all of these, it's basically taking all of the opcodes involved. It's doing some sort of calculation by referencing what the cost of every single opcode is, and it's adding that up, and then it's saying, okay, to do all of that, it's going to cost you this amount of gas. So basically, if you were to change this because you wanted it to be cheaper, so say I change this to 200,000, it brings the price down, but the problem is that the contract no longer, the transaction no longer has enough gas to execute all of the steps in that transaction. So your transaction is going to fail. Now, that's pretty interesting. I mean, in terms of you've never understood the gas limit, but where things get sort of, interesting again is that let's look at the max fee and the priority fee in terms of when you make a transaction. And this is obviously what happens when gas wars happen, right? Is you say you and me want to both buy this NFT at the exact same time. What happens if we click confirm at exactly the same time? What happens is both of our transactions go into the mempool, and then we have a group of miners who are looking at the transactions in the mempool and are going, I'm a miner. The reason I'm mining is because I want to make that, I want to make, the reason I'm participating as a miner in the network is because A, altruistically, I want to help secure this decentralized network, but B, I also want to make money and be rewarded for my efforts. So the way that miners get rewarded is they have a look at the mempool and they say, right, look at all the transactions that they see, okay, here's HODL's transaction and Soloist's transaction. They both want to buy the same NFT. How do we choose which one to process first? So the miners don't know who we are. They don't give a shit whether they process mine or they process his first. The thing they look at is they go and look at the price of the gas. So the miner looks at the transaction and it says, okay, well, HODL has gone and set his max fee to 150, whereas Solos left his as 111. Therefore, it's going to be more economically advantageous for the miner to process the transaction that has the higher fee because they're going to make more money out of it. So when you have a gas war, what's happening is you have, say, 10,000 people who are competing to mint 100 NFTs, and the top 100 transactions that have the highest fee are going to get paid the most, or going to get their transaction processed, because the miners want to make the most amount of money available. And if they have a choice of 10,000 transactions to process, it's kind of obvious when you think about it that they're going to choose the 100 that they're going to make the most money out of. There's sort of a new, in terms of sort of like one of the new EIPs that's come out relatively recently, which is an upgrade to the Ethereum network, is that you can also include a max priority fee, which is a way of sort of bribing the miner and saying, in addition to the gas fee, this is what I want to pay. So just to go back quickly to how the gas fee works. So if we were going to make, let's say this transaction is going to cost, it's going to use a total of 253,000 gas. So let's take this in here. Let's do like some basic calculations. Actually, this is kind of fun when you go and do it with actual transactions. So let's go and have a look at, for example, these were some transactions that happened with the humans. So let's maybe go look at the total. Maybe we'll go to the last one, and we'll look when somebody. Okay, so this is when people were minting humans. So if you go to Etherscan, you can see all of the details of every transaction. So what's interesting here is you can see, okay, in our contract, it took a total of 130,000 gas to process the transactions to mint the number of, however many humans you wanted to mint. So let's go and record this. So the gas total, or the gas used was this. Then let's go and have a look at, he set the gas price to 283 Gwei. gas price 283 GWh. You can see that was the max he was willing to pay, and what he ended up paying were two different things. So what's interesting is now you can go and say that, well, we know that the gas used was 131,896. So let's go and get a calculator. So let's say it was 131,896 units of gas were used. He paid a total of 283 GWh per unit of gas. So that comes out to a total of, what is this? 37 million GWh. So that's spent is 37 million GWh. So if you go and look at Etherscan, that's how this gets calculated, right? So I'm not sure if you're aware of the unit conversions, but 1 ether is equal to, that's 10 to the 18 Wei. So Wei is the smallest unit of ether. So 1 ether is broken down into, I don't even know how to say that number, but it's basically 10 with 18 decimal places, or sort of 18 to 18 decimal places, yeah, is how it's represented as a single ether. So 1 GWh is essentially, so one, get rid of this, make it easier to read. So 1 GWh is a gigagwei, which means that 1 gwei equals a million wei. So basically, if we were going to cut that off, when you go and look at the transaction, okay, so let's see. So we said this works out to 37 million gwei. So if we were going to move, if we were going to convert this from gwei to wei, then that would give us the ether amount. So you can go and see here that 0.037 ether is what you ended up spending on the transaction fee. So that's what we worked out here, is 0.037. So, you know, this is not, it's not rocket science. It's not something, but hopefully it just helps show that all of these crazy numbers that you're seeing kind of actually make sense at the end of the day, and that it's possible to work out the transaction. And what I just find really interesting about this is that when you break it down, it actually becomes really incredible how transparent Solidity in the Ethereum ecosystem is, where you can work out down to the tiniest unit what it costs to run a transaction. Where we debugged this? So if you were to go through and add up, you know, if this is going to cost, if 1 ether is 10 to the 18 wei, if this particular opcode costs 2 wei or 2 gwei or whatever to execute, by the time you've added all of those up, what you're really getting to is the amount of gas used, which is the gas limit. And if you multiply by that by the gas price you choose to set, then that's what you end up paying for the transaction. So that's kind of a really interesting way to just see how everything works at like a really low level when it gets broken down. And one more sort of interesting thing I wanted to just share is that if you go and look, so this happened with the Humans project, is we had a slight issue with our website where the website didn't tell people that, or it incorrectly told people that the collection still had tokens available when it minted out. And what ended up happening was like that small bug on the front end caused a lot of people to try and mint, and they weren't, and the transaction ended up failing because there were no tokens left to mint. So what happened is the miners would execute the transaction, it would run through the code, and then it would get to a point and say, oops, there's no transactions left. So therefore, or there's no tokens left, so therefore it reverts the transaction, and the person obviously doesn't get to mint their token, but then they, they sort of have a huge outcry, and they're like, well, now I've wasted, so let's look at this person, for example. This person would have they attempted to pay 0.025 Ether to mint one. So they see this, and then they go, MetaMask shows that it fails, and then they go, oh man, like I went and now I lost my 0.025 Ether, so, you owe me this back. It's like, this was in my wallet and now it's gone, to owe me back. But in reality, the only money that they ended up losing was the 0.003 Ether that it cost to process that transaction up until the point where that transaction failed. So yes, they lost a tiny bit of money on lost gas from the failed transaction, but you don't lose the whole amount. It ends up, you only lose the amount that gets spent getting to that point in the contract where it says, okay, well, from this point onwards, you can't continue because there's no tokens left. And something that we had to go and sort of try and show to people, or at least try and educate people on, is that when something happens, MetaMask is only going to record the transactions that MetaMask is involved in. So if I try and mint something for, 1 Ether and it fails, and then somebody, goes and sends me back, 0.05 or whatever the transaction, that 0.05 isn't going to show up as a transaction in MetaMask because it wasn't initiated through MetaMask. So a lot of people were coming back and saying, we lost a lot of money off of these failed transactions. You need to refund me like the 0.1 ETH for the 4 that I was trying to get. Actually, maybe let's see if we can find one of those, because that was like the most common use case. Is someone would try and mint 4. Let's see. Where's someone who tried to create 4? Okay, so for example, like maybe this person, they tried to mint 2. So they tried to use 0.05. So their transaction failed, and they would come, they come and they say, and it's not through their fault, they obviously just don't understand how things work, but they come and say, hey, I lost $130 because I attempted to mint 2 and the transaction failed. Where in reality, they only ended up losing $8 through the failed transaction. And, people, you show them this evidence and you say, look, this is the blockchain, and it's all of the data is available for you, and you can see here that the transaction fee is 0.03, and this is what was lost. Not understanding how things work, they come back and they say, no, my wallet balance was X, then after the transaction it was Y, therefore this is how much you owe me. But the beauty of the blockchain is that the blockchain never lies, and all of this information is available. So you can actually go in when you're looking at a transaction and you can view the state of the blockchain before and after. So you can see this is the address of the person who was trying to mint. Before the transaction, their balance was 0.3203. And you can see after the transaction, their balance was 0.317. So the balance only changed by a total of 0.003. And that's really important, because if you go and look at the failed transaction, it shows you that the transaction fee itself was 0.003 or 0.03, but the actual value that you were trying to transact, the 0.05, this wasn't taken off of your account. So this is just really interesting, sort of when you start to understand the mechanics and how all of these values are calculated. That, in fact, this is one of the beauties of the blockchain, is all of that information is there for you to see and to understand. The problem is that it's pretty, it can be pretty complicated, and a lot of people don't understand how gas works, how it works in relation to contracts and sort of executing code. But hopefully going through this process has been a little bit enlightening. I know we didn't get to cover as much Solidity and smart contracts, but one of the resources I will point everyone to, and I'm assuming because everyone is here and involved with NFTs, Most of the interest is around smart contracts and NFTs. So two great resources are obviously OpenZeppelin, like I mentioned. They provide all of the base contracts and the standards for so all of the token types that you want to create. And what's really useful is they also have a wizard that if you want to create your own, say, ERC 721 smart contract, they have a way of doing this interactively. And you can just go and create everything you want here, and it'll give you it'll just give you the boilerplate code. I mean, obviously, I hope that nobody goes and takes this and mints an NFT collection straight from it, but it's a really good place to start. And as you'll see, they link directly to Remix, so you would be able to, create the base for your contract, open that exact one in Remix, and then, hey, look, I have the start of a very basic contract that I can then compile and I can deploy. What was this complaining about? Contract may be abstract, not implement experience methods. Oh, okay, well. Interesting that it doesn't work off the bat, but interesting. Oh, I'll have to look into why that doesn't work straight away, but yeah, that's kind of it. Sorry, it was packing a lot of information into a relatively small amount of time, and I definitely kept everyone longer than I'd planned, but hopefully it was insightful and you managed to learn at least one or two things. I'm more than happy to stick around for a minute or two if anyone's got any questions or anything that I was talking about isn't clear or anything to follow up. I'm happy to stick around, but if not, thanks for joining, and hopefully those who are watching the recording will find it useful too. Okay, let me see. Permissions, give everyone. Let me add humans to this and then give them the ability to use voice activity. Sure. Does it? Yeah, yeah. I'm happy to do that. Does that? I tried adjusting the permissions. Is anyone able to talk now? It's pretty annoying that that wasn't done by default, so I apologize. I don't know. I see Julius, you're unmiked, or you were unmiked if you had a question. Oh, there we go. Sorry about that. Didn't mean to like mute everyone. The crypto lords. Cool. Let's have a quick look. Yeah, I've got it here. So, okay, it's using a proxy, which is interesting. So I wonder if they're doing something interesting with upgrading it at all. Interesting. This just looks like the proxy contract. Are these two different ones? Yeah, they look different. Let's see. Let's bring this one in. Yeah. So contract wrapper is proxy. So the proxy is basically pointing to another address, which is interesting. So basically this contract is pointing to another contract. And let's see if we can find where that is. Address slot, let's see if that's available publicly. It's a Merkle proof, that's obviously for the whitelist. Let's get down to the actual contract. FT art generation implicit. Interesting. So it's upgradable. Let's see. Affiliate of. Total supply. Referral map, referral mint. That's interesting. Referral's not open, cap's not set to 0. Interesting. So it looks like you have to get referral. This at least allows you to be referred by someone. Or show it if you get referred, it's obviously maybe some way of sort of like rewarding people who do refer people. The Merkle route, so this is for anyone who's on the white list or allow list. Mint all. So that's an owner function that lets them mint weird. This lets them mint the latest token, I guess. Mint payable pre-mint checks. Open equals true. So for example, like with this open equals true, this you could just have, you could go and read. I mean, this is what happens to a lot of contracts, is that this mint is controlled by this Boolean. So it's basically saying if this value is true, then you can mint. And what happens is that what they usually do is they'll go and set, they'll have like they'll say, in our Discord, we'll tell you at 2 p.m. when the mint opens, and then they'll go and like submit the transaction to open it, and then, it'll take 30 seconds or a minute to mine, and then they'll go in the Discord and say, hey, the mint is now open. But what can happen, or what does happen, is that people have bots that are just reading, they're constantly pinging the contract, so that as soon as this variable changes from false to true, the bots know that the mint is now available, and then the bots start like very rapidly minting. So it's a little bit of a disadvantage in terms of doing it that way, but also, what is the pre-mint checks? Whew, yeah, it's yeah, I mean it's definitely a whole topic. I mean, it's also one I don't know the exact answer to. I mean, there are some things that you can do, like for example, for this, when you set this, so they should have a function here that sets. They'll have a function that sets, so it's probably not open. Why do they set this? So update pre-sale. So for example, if they could set, so if they were able to set this function using Flashbot, then it wouldn't let bots backrun that transaction. So that would give, at least people a little bit more of a time. But yeah, it's hard. It's like, I actually don't know if there is a way through a public sale mechanism that you can prevent botting. I mean, the one thing that people do that's, you know, a method is that, so what a lot of, there's sort of two types of, you can have sort of multiple type of bot attacks, but there's one attack where, or exploit, or I guess just method where people create a specific contract that mints, that handles the minting, and then there are people who just sort of like run bots off of servers which handle the minting. And at least the way to stop, you can prevent contracts from minting by checking where the origin of the message comes from. And that basically you can check whether or not a contract sent that message. And then so you can stop contract bots. So that's pretty interesting. That's how the Adidas mint pass drop was botted. Like some guy came up with this really super smart way of minting. I don't know, he minted like hundreds of mint passes using a bot that had like a kind of like a re-entrancy style attack where it let, he would like create a new contract from the contract and then mint with that, and then like he would just sort of keep doing that in a cycle. So he managed to exploit the contract that way. But that only that you could prevent that from happening by saying, by checking the origin of the message, the sender, to make sure that it's not a contract. But that's also somewhat problematic because it prevents then, other things like multi-sig wallets and things that are actually contracts that might want to mint, then you sort of create problems for that. So I think there's always trade-offs. But I mean, I think the only, at least the only way off the top of my head I can think to do it is that there is no real public sale, and that you have, everything essentially has to be, either through some sort of allow list where in advance what the addresses are. Because if you make it, publicly available, then anybody who's, then you're sort of subject to gas wars. It's like the person who pays the most for gas is the person that's going to get to mint first. So it's interesting. Update request token. Let's see what that is. Request token. Yeah, it's definitely, considering how many smart people are in the space and how often there are mints happening every single day. It's kind of interesting that nobody has come up with a foolproof way of, I think there's some of those services, I can't remember what it's called, pre-mint or something, that where you have to sort of like sign up. But again, that's just taking the approach of like every as long as every address is known, then you can prevent people competing. Um, but I don't really know anyway, other than doing that. So this is the one you say that is minting soon today. Hmm. Royalty info. So it's upgradable, which is interesting. I have an airdrop. Royalties built in. Is there a reveal mechanism? Update sale. See, so this is kind of what we were talking about earlier. Is they have an initialize function that allows them to set the max supply in here. They're using ERC 721A. Interesting. Yeah, so this contract is upgradable, which means they can change. They could change the code at some point, which is kind of interesting. So, I think this is obviously a debate that a lot of people have. Um, Smart contracts are supposed to be immutable. It's kind of like a debate on approach. It's like, is it really a if somebody can sort of change the code or the contents of the contract, is it really like an NFT that could potentially live on forever if the devs or the owners do have the ability to change it or adjust things? But I mean, I certainly understand as a developer, it's basically like if you something goes wrong or you make a mistake or there's a bug and like it can't be changed, like that's obviously a difficult thing to deal with. So no, it's just an upgradable contract. So trace upgradable. I'd have to look into. I haven't read what this ERC 721 upgradable spec is, so it would be interesting to see what they can do. Yeah, exactly. Mm-hmm. 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 So we had to do that because Mint that we had problems in the very at the very beginning with the pre-sale that MetaMask was incorrectly predicting or estimating how much gas was required. So you'll see if we go to the humans contract. I wonder if this. See, so this happened in the humans contract is that a couple of transactions reverted because the execution was out of gas. And the reason, let's see what they if it shows in the gas limit. So it was setting the gas limit at 70,000, where that clearly wasn't enough to execute the contract. But the I still don't know the reason for why MetaMask is doing that. The only thing I can really think of is that the people who this happened to were using an older version of MetaMask that wasn't taking into account sort of like the newer transaction types. But it was very weird. So what we ended up having to do is like we had to override. So when you from the front end, you can just leave MetaMask to make the call themselves, or you can set what the gas limit is. So we just overestimated what the gas limit was, and then that solved the problem. But it still doesn't explain to me why MetaMask had an issue estimating the gas limit. So doing that isn't going to make a difference because if this transaction needed 100,000 and you set it to 1 million, the miner doesn't get the fee for all 1 million. It only uses the 100,000. So I don't think I don't know this for sure, but I don't think the miners take into account the actual limit. It's sort of something that's like a black box for them because like if the transaction fails, the transaction fails. Or if it only uses 100,000 gas, it uses 100,000 gas, and that's what they get paid for. So the only thing that the miners prioritize is the base fee and then the priority fee. You should, as a rule, never touch the gas limit. Like it should be up to you know, the DApp or whatever you're using to either correctly, for MetaMask to correctly estimate it, or it should be set at a point that does that as well. Yes, for sure. Yeah. Hmm. Yeah, which I can never remember the name. Is it F gas calculator? There's one that has a nice, it's not this, I can't remember the name of the, mm, hmm. No, no problem. I think that's, that's what's kind of interesting about it is so that's how, exactly like Hogan was saying, is the fact that everything's sitting in a mempool and that's all publicly visible. That's how front running happens, is that there are people or bots who are constantly scanning the transactions in the mempool, and they say, for example, let's use a dumb example like Bay Area Yacht Club are going to drop another collection, and obviously that's going to be a highly sought after collection. So what people do is, instead of bothering trying to mint, what they do is they watch the mempool transactions in the mempool, and they go and see, and they say, okay, we know the contract address, so we know where people are trying to mint from. So they watch the mempool and they say, okay, there's a transaction. They're trying to mint a Bay Area Yacht Club. They've set the gas price to 300 as an example. It's probably going to be a lot higher based on the project, but they can then clone that transaction, set a higher gas limit, or sorry, not a higher gas limit, set a higher gas price, and send that transaction to the mempool. And then when the miners are sorting through the transactions, they'll see, oh, this one has one higher gas than the previous one, so we're going to mine that one first. So that's essentially, in a nutshell, how front running works. I mean, that's a very simplified explanation, but it's basically just a case of people watching the transactions in the mempool and then imitating it, imitating the transactions, but giving them, paying either a higher priority fee or a higher gas price, and then that encourages miners to process those transactions before the originals.